Welcome to part 2 of our optimization section. Here we will just get through some examples. In example number 1, we have a common type of optimization problem. We have a 20 by 25 inch sheet of tin, and what we want to do is cut congruent squares from the four corners of that sheet of tin. Then, once those corner squares are cut out, we will bend up the sides, fold up the sides, and create an open top box. Now we want to know what size square do we need to cut from those corners so that we'll maximize the volume of the box. So in most optimization problems, I recommend starting with just a drawing. So in this case, this is hard to draw on this screen, so I got a picture. And we have this 20 by 25 sheet of tin here, this outside rectangle. Then we have these four corner squares that have been cut. And what remains is this like bolded black part here, that when we fold up these four sides, it creates this open top box. So we've gone from this two-dimensional piece of tin that's a rectangle into a rectangular prism with no top. So we want to figure out what size square do we need in order to maximize the volume. So let's first get labeling this first picture here. We know that this entire side, this is the longer side, so we'll say that this is the 25-inch side, and the shorter side is 20 inches. Then, because the variable, so these like numbers don't change, but the variable piece of information is the size of the square that we're cutting. So let's call the sides of that square, because they could theoretically be larger, smaller. We just want to know what value do we need to cut, what length here, in order to maximize the volume of this box once we fold it up. So these side lengths here are called X. So X, you know, this one's X, this one's X, this one's X. They're all X. I might have went a little overboard here, but I do want to show that the length that we're cutting here and into here to make that square. The length is X because it is a square. So let's think about what the dimensions now of this box actually are once we've cut away that X. This new bottom side here is not 25 anymore. 25 was the entire thing. But what have we taken away from this entire length of 25? We have taken away an X here and an X here. So we have taken away 2X from the total side length that once was 25. So this new dimension here, the one that got folded up, rather right here, this bottom piece here, or this right here, is 25 minus 2X. So this length is 25 minus 2X. You can call that the length or the width. It does not really matter in this case. And then the other side, which initially was the 20-inch length of the side of tin, we have again taken away an X here and an X here. So similarly, this length right here of our box is 20 minus 2X. Now, in order to find the volume of this new open-topped rectangular prism that is just a box, we need to find the length, the width, and then also the height. Multiplying those three values together will get us volume, which is what we want to maximize, or in the calculus sense, optimize. So what is the height of this box that we folded up? Well, the piece that got folded up was these side pieces right here, these X values that we cut. They got folded up. So the height of our box is just X. So those X values are the height of the box all around. So our optimization equation is the volume, because that is what we want to maximize. We're looking for the X value that maximizes the volume. So let's write out that equation for volume using our picture that we just labeled. Since volume of this box is going to be length by width by height, and multiplying those three, we have the volume in terms of X is the length, which is 25 minus 2X. The width, 20 minus 2X, again, those are interchangeable, we're multiplying them anyway, times the height, which is X. So we now have our volume equation, and this is the equation that we want to maximize. Now, in order to maximize an equation, we need to do some calculus on it. But before we get there, I'm going to just do some algebra, and that's going to come in the form of multiplying through here. In this first step, I have multiplied the 25 minus 2x by the 20 minus 2x. This x still remains out here. Let's combine some like terms and then distribute the x through. So I have combined the minus 50x, the minus 40x to the minus 90x, and then I distributed the x through to all three terms. And then just for my own peace of mind, I like writing polynomials with the term with the highest degree first. So I just arranged the order here. So what we have done so far is we have drawn a picture of our scenario, and then we figured out the equation that we want to maximize or minimize, or just in general, to optimize. That equation is given by the sentence asking this question: what size square will maximize the volume of the box? Therefore, we needed to come up with the volume formula, because that's what we want to optimize, which is right here. It is in terms of the variable that we're looking to find, which is the side length of the square that we're cutting, and that is x. Now we can do the calculus on this volume equation, or formula rather, by figuring out the maximum value. So what value of x will yield a maximum volume? That means that we need to find the critical points and test them using either the first or second derivative test. In order to find the critical points, we need to first take the first derivative. So we need to take v prime of x. That will give us 12x squared minus 180x plus 500. Then we need to set that to 0 to find the critical points. Setting this equation to 0, in that step, we can also factor. We can factor out the GCF of 4. From here, we have a quadratic trinomial still, but it's just a little bit simpler since factoring out the 4. This 4 is not going to provide us with any solution as it is a factor, but it doesn't have an x with it. So we have this quadratic trinomial. Can we factor it? Maybe. But because these numbers are pretty big, I'm just going to opt to do the quadratic formula. So that comes in the form of setting each factor to 0. Again, that one doesn't provide any solutions. And solving a quadratic trinomial, we could either factor it if you'd like to try, or we can just use the quadratic formula. From here, once we've plugged in our quadratic formula, we have a discriminant value of 525. That is not a perfect square, therefore the answers here will be irrational. We end up getting two answers, of course, from the quadratic formula, and one is that the x value, or the length of that cutout of the side of the square, would be 11.2, and then the other is that our side length of our square would be 3.68. Let's take a look at this problem from the start and see if either one of these values makes sense, and if one, none, or both of them make sense, we can test to see which one will provide a maximum volume. This means we have to think about the domain of our problem, so I brought down the picture. If we take a look at what the restrictions of x are, we definitely have some. You know, x can't be less than 0 because it needs to exist, and we can't cut something that is a negative amount of units, inches rather, which is what this is measured in. And so that means that our x value at least has to be greater than 0. Then on the higher side of x, right, what is the largest value that x can take on? Well, let's look at the smallest side, which is 20 inches long, and we want to think, well, we have to cut and cut from both ends, and if both my cuts need to be the same length, that means that at most I could cut 10 inches on each side. Now that would be cutting the entire side, but that is the maximum value that we could cut. So that means that the domain of this problem is from 0 to 10 inclusive. Now that means if we look back at our potential solutions over here for the value of x, 11.32 doesn't make that cut. It's not in the interval. Therefore 3.68 is our only critical point that lies in the interval. I'm going to perform the first derivative test to see which one, or to ensure that 3.68 will provide us a maximum. I also am going to double check that plugging in either one of our endpoints, 0 or 10, will not yield a maximum volume. Let's do that first really quick. The volume of 0, if we either think about it, if x is 0, that means we don't even have a box, we didn't make a cut, therefore the volume would be 0. We can look back at our volume formula, x equals 0 will yield a volume of 0. The same thing for 10, although it's not as easily visible. If you take a look at if x was 10, if you look here, if we multiplied these three together, which is how we got this volume, 20 minus 2 times 10 is 0. So if one of our sides was 0, that means our volume would be 0. So the two extremes in the x values provide a volume of 0. That means I want to check and make sure that our critical point, 3.68 for x, yields a relative maximum point. I'm going to perform the second derivative test to do this. So if we take a look at our first derivative up here, we're going to take the second derivative of volume and then plug in 3.68 and make sure that it's negative, meaning 3.68 would have yielded a maximum value. So finding the second derivative will give us 24x minus 180. I'm going to plug in 3.68 and see what type of answer we get out. I know that 24 times 3.68 is less than 180, so if we subtract, it'll give us a negative output. Because our second derivative is negative at 3.68, it means our graph was concave down there, meaning that 3.68 does yield a relative maximum value. So according to the second derivative test, yes, 3.68 would be the cut that we need to make in order to maximize our volume. So going back to the very beginning, what size square will maximize the volume of the box? The size square would be having a side length of 3.68 inches. I have plugged in our volume formula into Desmos, and we can see that it's clearly a cubic. It does have a relative maximum and minimum point, but note that where the relative minimum occurs would have been at that other critical point that we found, 11 something, which is over here. That provided a relative minimum, but was outside of the implied domain. We only care about volumes that are positive. Note that the domain that allowed us to do so was in between 0 and 10, which would yield positive volumes. So this is the part that we care about. We do in fact have a relative maximum here, and it occurs, of course, at our x value of 3.68. Example number 2, we have a rectangle that will be inscribed under one arc of the sine curve. We want to know what's the largest area the rectangle can have and what dimensions will give that area. This is an optimization problem because it's asking about the largest area of a rectangle. That's another way of saying the maximum area. So we are going to have to figure out, after drawing, the area formula for this rectangle. We want to have it in terms of one variable, and then we are going to perform calculus on it to find the maximum. So here is the sine curve, and so again, just drawing something is the best way to start. So naturally I found a picture. And so we want to inscribe the rectangle under only one arc of the sine curve. So let's take a look at just this first arc of the sine curve here, and then I will crop out the rest of the picture. So inscribing a rectangle means fitting it as snugly as we can. So one place that this rectangle could be is here. It's inscribed, meaning it's going to touch at 2 points. Another possible rectangle that we could have would be here. I'm just drawing different rectangles. There's an infinite number of possibilities. But what we do notice, the similarities between these rectangles, are that the top two, or the height rather, is determined by the sine curve, whereas the base is determined by the distance between two x values. The reason we care about that is in order to find the formula for the area of a rectangle, which is what we're going to have to optimize, the formula for a rectangle is just base times height. So the base is the distance between x values, whereas the height is the y value, or the output of our sine curve. I have gone just with a single first arch here, so this is 0, 0, and then this would be where the sine curve first hits back to 0 again, which if we think about on the unit circle is at pi. So right here the x value is pi, and right here it's 0. Now this first point here, I went out x units and up onto the function, so the coordinates of point A here is x comma sine x. It's output. Then for point B, we have gone another distance, but let's think about how far that distance is. Since the sine curve is symmetrical and this distance is x right here, then this distance is also x. So to here, this x coordinate would be going all the way out to pi, but then subtracting this distance in between. So this x coordinate right here is pi minus x. Now, since the x-coordinate is pi minus x, the y-coordinate could very well be sine of pi minus x. However, because of the symmetry of the sine graph, it's still just sine of x. The sine of pi minus x and the sine of x are actually the same. We can see that the height here, because it's a rectangle, is the same. So I'm, out of simplicity, just going to call the height sine x again. Now, since we have drawn the situation, the next thing that we want to do is write out the equation of what we're trying to optimize. We want to get the largest area, and so we need the area in terms of x of our rectangle. Area is base times height. So the base here is this entire length out to here, subtracting this length right here. So we want this full length from 0 to pi minus x minus this piece, since we only want this orange length. So it's pi minus x, or pi minus 2x. We can also think of that as this entire distance here is pi. This piece that we don't want and this piece that we don't want are both x. So it's the entire distance pi minus 2 of those x's. So far we have the base of the rectangle, then we want to multiply by the height. The height is sine of x. So now that we have the equation that we want to maximize or optimize, we can actually perform the calculus on it. So that involves finding the critical points. That means that we have to take a prime of x and find a prime. We are going to be using the product rule, so I'm going to do u times v prime first. So u is pi minus 2x, and v prime is going to be the derivative of sine of x, which is cosine x. Then I want to do v times u prime. U prime is going to be the derivative of pi minus 2x. Well, this is two terms, so the derivative of pi is 0, since pi is a constant, and the derivative of minus 2x is just minus 2. Here I have cleaned up a prime, and we want to set it to 0 to find the critical points. Now, this is not one that we can solve by hand, so we are going to be using Desmos. Before we take a look at the graph of a prime, what I want to do is figure out the domain so we know where to look. Our x values are under this particular sine arch. That means that they're between 0 and pi. So our domain is that x needs to be between 0 and pi. And remember, Desmos is not like in terms of pi, rather, so we're going to be looking about to 3.14. This is the graph of a prime, and we want to know where it equals 0. But let's make our search a little bit smaller and remember that x values can only be between 0 and pi. It looks like there are two spots where a prime is 0 in between 0 and about pi over here. Right here and here. Let's see what those values are. Our first one is 0.71, and our second one is 2.431. Because we have endpoints once again, and we have two critical points that we found from the graph, what we can do is perform the candidates test. Again, there are multiple ways to test out these critical points, but because we have endpoints, we can definitely perform the candidates test. Although once again, just like in the first example, if we had an x value of 0, well, we wouldn't have a rectangle to begin with. And if we had an x value of pi, this point right here would be pi minus pi. Again, we'd have zeros. So these endpoints a lot of times are just the extremes, and they're not going to work out for these application problems. So this is what we know so far. An x value of either 0 or pi will yield an area for our rectangle of 0. And we can see that by plugging in, if we plugged in 0 for x, we'd have the sine of 0, which is 0 here. And then if we plugged in pi, we'd have pi, the sine of pi, which is also 0. So what we can do is plug in these other 2 points and see what our area is. Plugging in our 2 critical points yield areas of 1.122 and negative 1.122. This obviously doesn't make sense. So it looks like the x value, or x-coordinate, that would maximize the area of this inscribed rectangle, would be right here. So our answer is an x value of 0.71, And then we need to find, so a couple different things. We need to find the largest area that the rectangle can have and what dimensions give that area. Well, dimensions here are x by y, or base times height. So our largest area is this output here, a of x, which is 1.122. And since it's area, we want to write it in units squared. We do not have any particular units here, so I'm just going to write as units squared. So that's answering the first question. What is the largest area the rectangle can have? Now we need to give the dimensions of that area. Dimensions of the rectangle are base times height. This value here is not simply 0.71. That's this length. That's the x distance here. This is the base and this is the height of our rectangle. So the base of our rectangle is pi minus 2 times 0.71, and the height of our rectangle is the sine of 0.71. Using our calculator, we can find these values. So plugging in 0.71, the x value that maximized the rectangle's area, to the base and the height was 1.72 units by 0.65 units. So with optimization problems, it's sometimes not enough to just find the x value that optimizes, or maximizes whatever the problem is. It's answering the question using that x value. So giving the answer of x equals 0.71 is not sufficient. We have to answer the questions. So far, we've done 2 optimization problems. Let's try to break down the process as much as we can so far based on what we know. What has been the first thing that we've done for each one of these problems? The first thing is obviously reading through it and seeing what we need to do, but the big first thing is drawing a picture. Drawing a picture allows you to visualize exactly what you're doing and to ask, what is the question asking me to find? That is usually your X. So drawing and labeling either a picture, graph, whatever's necessary in order to figure out what do I need to find. The second thing that we did in both cases was to write out the formula or equation that needs to be optimized. In example 1, that was the volume of the box, so we had to write out the volume formula for that particular rectangular prism, length times width times height. For example 2, it was the area of a rectangle, so for that particular problem, what we needed to optimize was area of a rectangle, base times height. It's whatever goes with that particular problem. These 2 parts, weirdly enough, are the hardest part, just getting started. Because once you have this number 2, you can do the calculus. At this point, you are ready to find the maximum or the minimum. You're ready to use calculus to optimize. Now, what does this process look like? Well, already in 2 different examples, it's looked a little bit different, but the general way to solve it is the same. Like your end goal is the same. You want to take the first derivative, set it to 0. That gives you your critical points. Remember, critical points can also be where the first derivative is undefined. We just haven't had an example like that yet. So we find our critical points and figure out if they fall into the domain of our problem. And in order to figure out whether those critical points that work are minima or maxima, we can do a few different tests. For the first example, we performed the second derivative test in order to figure out which x value yielded a relative maximum. In the second example, we use the candidates test. So there are a couple different things that you can do. Those different tests that we can perform are the first and second derivative tests, or if you prefer, if you'd like to also test the endpoints, which is important, but most of the time they end up yielding zeros because they are the most extremes, we can also use the candidates test like we did in example 2. There are always a few different ways to do these types of problems, and it's really whatever test you prefer. Finally, the very last thing is to make sure that you're answering the question that's being asked. In example 2, this was pretty important because we did not just need to find the x value, we needed to actually answer the question. What was the area of the rectangle and what were the dimensions of the rectangle? Not simply what is this x value. You have to remember that the majority of people around you are not as good at math as you are. And someday in your future, you may or may not have a boss that kind of falls into that same category. They don't really care that x equals 0.71, like in example 2. That's not important. They want to know what's the maximum area of this rectangle, or what is my maximum profit going to be. They don't necessarily care how many units you need to sell in order to make that happen, or at what time of the day, whatever that is. All that behind the scenes math, that doesn't matter anymore. You have to make sure at the end of the day that the final answer is to the question that's actually being asked. In example 3, we are a product engineer and we're working with the marketing team to design this 1-liter can that is made from some recycled plastic. It's going to be a right cylinder, and so we need to minimize the amount of plastic that we're using. We need to know what should the dimensions of this 1-liter can be. And for a note here, 1 liter in a volume sense is 1,000 centimeters cubed. The first thing that we want to do here is draw a picture. What is a right cylinder? A right cylinder is one that stands upright. For real. It's not slanted at all. So this is what a right cylinder looks like. The first picture that I'm actually drawing. There we go. Not too bad. And let's label this. We care about basically the surface area of this if we're thinking about it, because we want to create this. It's not going to be filled with plastic. It's just going to be made from plastic. So we care about the surface area. Now, the formula for surface area of a cylinder is right here. And if you do not remember that from geometry, there is Google. So we have the 2 circles that make this up. And then if you were to roll out this middle part, it forms a rectangle, and it's the height times the length of it, and the length of it is the circumference of the circle, which is 2 pi r. So that's pretty cool. That's where this comes from. So it looks like the variables that we have in here are r and h. So labeling, that's the height of the can, and then the radius obviously is just this half of the circle. Now here we're kind of running into a problem. We actually have the surface area formula, which I just call SA, and it's in terms of 2 different variables, r and h. We need to get it down to 1 variable. In order to do that, we need the same number of equations as we have variables, which is 2. So we need 1 more equation in order to do some substitution to get it down to 1 variable. We're going to be looking at the other information that we're given. We know that this can needs to hold 1 liter or have a volume of 1,000 cubic centimeters. Therefore, the volume of this right cylinder needs to equal 1,000. So we can come up with another equation using this extra info. Now, what is the volume of a right cylinder? It's base times height, basically, meaning the area of the base, area of the circle, times the height. It's as if you were to stack an infinite amount of these circles until you reach this height. So it's pi r squared times height. So the volume is pi r squared h. Now we want that volume to equal 1,000. So instead of V, I'm going to replace it with 1,000. And again, we're in centimeters. So the reason that we care about this extra formula is so we can do some substitution. What I'm going to do is solve this for h and then replace h with what it equals. So let's solve this guy for h down here. So we divide both sides by pi r squared. We have that h equals 1,000 over pi r squared. So we're going to take what h equals and substitute it in for h into the equation that we want to optimize. All right, so far we've drawn our picture and found the equation that we want to optimize, the surface area. But since the surface area formula was in terms of 2 variables and not 1, we couldn't optimize it very well. So instead, we used the extra information that we were given to make another equation. Solving that equation for h, we can now substitute. So let's rewrite our surface area equation, which I am now going to call something better than SA. I'm going to call it S of R, surface area in terms of the radius only, because we're going to be replacing h with 1,000 over pi r squared. So the surface area in terms of r is now 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Replacing. Now we can cancel a little bit here. this r and one of those r's can cancel, and we can multiply the 2 times 1,000. So we'll have 2 pi r squared plus 2,000, and of course these pi's can cancel too, 2,000 over r. Now we have our surface area formula in terms of one variable r. So now we can optimize it. Instead of writing 2,000 over r, what I'm going to do in order to take the derivative more easily is write r to the negative 1. I'll do this calculus in orange. So we have s prime of r. Remember that 2 pi in general, is just a constant out front, rather a coefficient to the r squared. So we treat it as we would any other number out front. And so we're going to use the power rule here and multiply the 2. So we'll have 4 pi r to the first, or just r. Then, same thing over here, we'll have minus 2,000 r to the negative second, which I can write as over r squared. Now we want to find the critical points by finding where the first derivative, s prime of r, is equal to 0 or is undefined. Looking at this real quick, I note that this would obviously be undefined if r was 0, since r squared is the denominator. So I already know that one critical point is r equals 0, because that's where our first derivative is undefined, since r squared is in our denominator. Setting it to 0 to find the other potential critical points, we'll have 0 equals 4 pi r minus 2,000 over r squared. I'm going to add that 2,000 over r squared to both sides. Next, we can cross multiply. We can put this over 1 if that's helpful. So we'll have 4 pi r cubed equals 2,000. Subtracting 2,000 so we can factor, or you definitely did not have to do it that way since 2,000 did not have an r in it, but I like the factoring way. I'm going to factor a 4 out, so we'll have pi r cubed minus 500 equals 0. So 4 equaling 0 does not provide us with any solutions. And then we have pi r cubed minus 500 equals 0. So we'll have that r cubed equals 500 over pi. And then we'll have to take the cube root. Now clearly this answer is going to be some crazy decimal, so we should definitely use our calculator. Taking the cube root of both sides looks like this. So we end up with r is approximately 5.41. Now we don't need a plus or minus because we're taking an odd root. Now for this problem here, it's a little bit harder to figure out what the implied domain is for r. Clearly r needs to be a positive number since it's a measurement, but it's hard to know kind of a maximum that r can be. We know that definitely it can't be over 1,000 because if we squared it multiplied by h and pi, it has to equal 1,000. So we don't really know the domain super well, but we do just know that r needs to be greater than or equal to 0, just because it's a radius. So 5.41 is a totally plausible value for the radius. Let's test it out. And in this case, since we don't really have well-defined endpoints, I'm just going to use the second derivative test to ensure that this value of r would indeed give us a minimum. Using the second derivative test, I need to find the s double prime of r. Here's s prime of r, so I'm going to just take the derivative of this right here. The derivative of 4 pi r with respect to r is just 4 pi. Then this term right here is minus 2,000 r to the negative second. Using the power rule, we'll have the negative 2 brought out front, and that'll be plus 4,000 r to the negative third. So that's our second derivative. I can plug in 5.41 here and we'll see what type of value we get. Well, this is always positive, and 4,000 divided by a positive number would be positive. Therefore, the second derivative at our critical number of 5.41 is positive. Because the second derivative is at 5.41 is greater than 0, that means our graph is concave up there. Concave up looks like this. Therefore, we would have a relative minimum at r equals 5.41. So yes, the second derivative test tells us that a radius of 5.41 centimeters would in fact give us a minimum surface area. Now, because we found our radius of 5.41, does that answer the question? Our question was, what should the dimensions be? Well, the dimensions of a right cylinder are radius and height. So we have the radius, we need to find the height. How can we do that? Well, we already have a few different equations that relate height and radius. One of them's right here when we solved for height. So I'm going to plug in our radius value here to find the height. Plugging in, height is 1,000 divided by pi times 5.41 squared. That yields a value of 10.88. So our height is going to be 10.88 centimeters. Now the question only asked us what the dimension should be. It did not ask what the surface area would be with those dimensions, but if it did ask for that, we could totally plug in the radius and the height into the surface area formula from the start and figure out what that surface area would be. So once again, calculus has allowed us to answer this optimization problem. Our last main example, we'll talk about profit. Profit is the money we bring in minus the money that leaves us, or the cost to run the business. So profit is revenue minus cost. In other words, P of X, or whatever variable, equals R of X, the revenue, minus C of X. If we wanted to find the first derivative of profit, because we want to maximize it, or minimize it, I guess, in another world, we would take the derivative of each one of these, R of X and C of X, by the sum and difference rule for finding derivatives. Well, in order to find the critical numbers here, we'd set P prime to 0. That means we would have 0 equals R prime of X rather, minus C prime of X. And adding C prime of X to both sides would give us when R prime of X equals C prime of X. That's when we would have a maximum or minimum, again, profit. So the maximum profit occurs, or potentially occurs, any point where R prime equals C prime. Here we have a graph of profit. We have revenue and we have cost in red here. Revenue is in blue. Well, any time that their derivatives are equal, that would mean that the tangent lines would be parallel. They would have, their slope of the tangent lines would be the same. Since revenue in this case is linear, its slope is constant. So the slope of any tangent line is just the slope of the revenue curve here, rather line. The cost has tangent lines that are parallel to the revenue over here and over here. So there would essentially be two critical points. So note that their difference, the gap between revenue and cost, is maximized at those 2 points. It's either when cost minus revenue is larger or when revenue minus cost is larger. We like the latter more, because we want revenue to be greater than cost. So note that we either have maximum loss or maximum profit, in this case this would be minimum profit, when the two derivatives are equal to each other. So we found it algebraically up here that a maximum profit occurs when R prime equals C prime, and we can also see it graphically. Example 4 talks about this profit. We're given two equations, one for revenue and one for cost. We want to know what production level maximizes our profits. Well, we saw before that in order to maximize profits, we want to know when does R prime equal C prime. So let's find R prime. Since R of X equals 9x, R prime is just 9. That's not too bad. Then C prime over here is finding the derivative of the cost function C of X. Using the power rule, we will have 3x squared minus 12x plus 15. Now we have a quadratic, so let's get that to 0. So we'll have 3x squared minus 12x plus 6 when we subtract 9. Now factoring, we can take out a 3, so we'll have x squared minus 4x plus 2. Is this factorable? No. We need to use the quadratic formula. So solving using the quadratic formula will yield 2 plus or minus root 2 as our potential solutions. So once again, we have to take a look at, since this is an application problem, we need to take a look at what the implied domain is. We obviously cannot produce, since x is like number of units in the thousands, we can't produce a negative amount of units. So x does need to be greater than 0, greater than or equal to 0 as our domain. But we don't have a maximum on x. It's not capped anywhere based on this problem. So we don't really have endpoints. We just know that x needs to be positive. So both 2 plus root 2 and 2 minus root 2 are positive values. Now I'm going to write these as decimals so we can see them a little bit better. Now, how can we test these two out? One of them could definitely maximize profits, but one of them could minimize profits and actually maximize losses. We need to figure out what the profit formula is from the get. We have shown earlier that profit is revenue minus cost, and P prime would be R prime minus C prime. We have found R prime and C prime over here. R prime is 9, and C prime is 3x squared minus 12x plus 15. So simplifying this, P prime of x is 9, and then a little bit more work, and we found P prime. It's negative 3x squared plus 12x minus 6. The reason I do this is because we can either perform the first derivative test using these two critical points, or we can perform the second derivative test. I'm going to perform the first derivative test just because I haven't done that yet in this video. So performing the first derivative test using these two critical points, and actually 0 is our most minimum value for x. We have 0.58 is one of our critical points, and 3.41 is another. Both make our P prime 0 because they're critical points. Then we could plug in values here, here, and here. Plugging in 0.1, we end up getting a negative value for P prime using a calculator. We can plug in a value in between here, like the number 1. So if we did that, we'd have negative 3 plus 12 minus 6. That's a positive. And then plugging in a much larger value, like let's say 10, we'll have negative 300 plus a large number, 12 times 10, 120, not quite enough to get out of the negatives, and then minus 6, so we're negative again. So that means that our original profit function decreased, increased, and then decreased again. Because our P prime went from negative to positive at 0.58, there's a relative minimum at 0.58, minimizing profits, which means maximizing losses. Then because P prime went from positive to negative at 3.41, 3.41 is where a maximum occurs. So we actually have x equals 3.41 would give us a relative maximum, but a maximum nonetheless. Now we want to make sure that we're answering the question. What production level maximizes profits? Well, x is 3.41, but since x represents thousands of units, in order to answer the question, we would say an x value of 3.41 times 1,000, which is going to be 3,410 units, would maximize our profits. In this video, we have done 4 examples of optimization, 3 maximum problems and 1 minimum. We have used calculus along with a little bit of creativity in order to figure out how to maximize or minimize based on the specific problem. We also went through the process for optimization, which is found somewhere in the middle of the video. I hope that these examples help you. Good luck.